Another Step 2 mechanics question, 2007, question number 11 is also question 3 from the Step 2 mechanics support module. What we've got to get over here is point O lies in horizontal fluid, B 50 miles east, 50 meters, sorry, I guess that probably says east of O, projected 25 meters per second, an angle of arctan above the horizontal, and in a direction 60 degrees with OB. Now, how is that possible? Well, we can see in the next bit, I, J, and K. This is a three-dimensional problem. So it looks all in all a bit like this. You've got B directly to the east of O, and you're firing the thing vertically and sort of, so it's got an I component, a J component, and a K component coming out of the plane. So hopefully that makes sense. And of course, if I draw a line sort of going through the plane here, running along the plane, then this angle here is the theta that they were talking about. So that's the projected above the horizontal. So that's how much into the air it's going. And then in terms of from O to B, we can use this kind of shadow. We can think of this as from where the thing's being projected along. We can use that shadow to mark our 60 degrees. Relative to the line OB, which is what it talks about here. And this 50 refers to the fact that it's 50 meters away. So that seems to be our picture. And yeah, let's find the position vector at some time then. So, well, the K, actually, we can do position vector, we can talk about its speed, I guess, U, being having an A component, which is its I, which I'm going to say is going to the right like this. Its B is a J component, so that's going upwards, kind of not up the screen, of course, but upwards along the plane there, and then K is going out perpendicular to the plane. It's K component's the easiest bit to start off with. It's worth bearing in mind at this point, of course, that you've got an acceleration going on, which has no effect to the I or the J component, because those are both actually flat to the ground. It's K component in my world, K component coming out of the plane. That's the thing that's being brought down with a minus 10 meters per second. Anyway, it's K component is the easiest thing to do, because that's the bit here, right? And that's literally just 25 sine theta. Now, if theta is arctan of a half, you can move that over there, and you can draw a little triangle and make this a root 5. So sine of theta is 1 over root 5. So that's all actually relatively easy. And then we can rationalize this maybe times by root 5 or root 5. And you'll end up with this here, 25 over 5 gives you this 5 here. So that's its vertical component, its K component of its velocity. I'll deal with the position vector bit in a second, but that's the K component of velocity. Now, what about the I and the J component of velocity? Well, at this point, we can kind of tilt our heads and imagine that we're just looking at this from directly above, right? And completely ignore the K components. In that case, this line here, we could think of as just the place where the speed is running along. And we can just do 25 cos 60 for this component and 25 sine 60 for this component. No, sorry, not 25, because 25 isn't the speed. But if I do 25 cos theta first, cos theta, of course, is 2 over root 5. 25 cos theta is this. It's just double the other one, of course. And then I can say, again, looking at the picture from above, ignoring all the k's and the 3D-ness, I've got my v now, and this will just be v cos 60, and this component will be v sine 60. So v cos 60 is going to be my horizontal component, and of course that's going to the left, so I'll just make it negative, and that'll be that. Cos 60 is a half, of course. And then my vertical component, which is going upwards, so I'll say it's positive, is 10 root 5 sine 60. Sine 60 is root 3 over 2, so you end up with 10 over 2 is 5, and then that times is to make it 15. Okay, so those are our components. Where do we get our position vector from? Well, at this point, we just need to think, well, okay, it's moving with a speed of minus 5 root 5 every t seconds. So, well, that's a speed. So obviously speed equals distance over time. Speed times time is distance. So I'm just going to need to do minus 5 root 5 t, except of course we're doing this relative to O, from O. So of course it'll start 50 away and then we'll take away that distance that it goes every time. And the J component is the easiest because we start at the zeros actually, if you imagine an XY axis kind of going through the plane like this. We start at 0 and then we're just doing 5 root 15 t because again, distance equals speed times time. And now the K component's the most complicated bit here, but we can use this formula, I guess. And I've just used the first bit of this formula for these two things because of course A is 0 across the I's and the J's. I've had to adjust this one slightly because we start 50 meters away. But for the K's, I'm going to have to consider this, right? So its speed is 5 root 5 times t plus a half times minus 10, which is minus 5, times t squared. So this will be our speed or our position, sorry, in the vertical space. coming out of the plane. So this will be our whole thing brought together, and that's about there. And now we're being asked to show that the distance from O is this. Okay, well, distance is just, of course, the magnitude of the position vector. So we just need to do this squared plus this squared plus this squared and square root it maybe. So we've got some point over here and we're looking for this distance. So of course we just need to do the x, or the I component squared plus the j component squared plus the k component coming out of the plane squared. It's just 3D Pythagoras, isn't it? So it's just this squared plus this squared plus this squared. Do a bunch of maths. I take out 5, obviously. So there are 2 5s to come out of this because there's 2 brackets, right? So take a 5 out of each, and that'll give you a 25, and you can do the same thing for all of those. Just makes it slightly easier. It's still a little bit of a mess. At this point, you think this is going horribly. How on earth have they got here? Remember, you're still looking at d squared right now. So you need to square root both sides. But how do you square root both sides? Well, it turns out that this, it's very helpful. Always look at the thing that they've given you. Just blag it. This is definitely this thing squared. I mean, you can check if you want, but I mean, it basically has to be because you want to square root them. You can only square root products, right? So now when I square this, I'm going to get 5 times just one copy of that, which is exactly what they want me to get. Just blag it. You know, if you get to this, you can check it if you want to, but it's, I mean, I would check it just to make sure you haven't made a mistake somewhere in here, but I think it works for me, so that's fine. When the distance is the shortest, okay, so we want to minimize this. The particles, we'll call it p. Okay, so how do we minimize this? Well, you could differentiate it. I decided to complete the square just for now, just because it's a quadratic, you know, you may as well. So halve this number down, take away the square of that, makes 5 over 4. And clearly this is minimum at t is root 5 over 2. So all I have to do is put root 5 over 2 into here. At this point, I'm also just going to say, just because this is helpful for the ending of this question, when t is root 5 over 2, this becomes 0. So the distance is 10 minus 5 over 4 times 5, which is 40 minus 5 over 4, which is 35 over 4. And I've just left it as that because I couldn't be bothered to work out what that actually is. Anyway, at this point, we just need to put root 5 over 2 into our position vector here, which will give us this. A lot of root 5s are very helpful here, right? So root 5 times root 5 is 5, times 5 is 25, and then just divide by 2. And that's what I've done for the rest of it as well. And I guess you can bring those things together and you get something that looks a bit like this. So good, that's where P is. So basically, P is like here, and we're going across this much, up this much, and then out of the page this much. And now, it's horizontal bearing from O. What that means is it's bearing when you just completely ignore the K component. So in other words, we're going across 75 over 2, we're going up the plane 25 over 2 root 3, and then we're going out of the plane this much, but that doesn't matter. What I'm going to say is let's look for this angle here, which is of course tan inverse of this number over this number. Very helpful at this point, these 2's will cancel. 25 over 75 is a third, and root 3 over 3 is 1 over root 3, which is the same, I guess, as tan inverse of 30. Or sorry, tan of 30. So therefore this is 30, but of course remember we're measuring a bearing from north. So if you imagine again just looking down on top of the plane, north will just go veering straight up, and then we just need this angle going around. This is 30, so of course this will be 60 here. So the bearing will be 0, 6, 0, I think, for that question. Okay, good. Show that the particle reached maximum height at P. Well, if it's at its maximum height, that means its K value isn't changing, or its K value has, if you differentiate its K thing, it will be 0. Is what I said. So here's its K, here's the function for its K units. So if I just take that and call it the height, and then differentiate, I can set that to 0 to find what T value gives me its maximum, right? So of course I can solve that, and I'll get this, and that happens to be the same T value for which you were at P. So therefore it reaches maximum height at P. It's happening at the same time. So therefore it's reaching maximum height at P. So there we can say that. And lastly, when the particle is at P, so let's just pretend P is here, someone fires a bullet directly at it, traveling very fast. Ignoring the effect of gravity on the bullet, which is going to be very helpful, when it passes through P, show the distance between P and the bullet is roughly 3. So what we need to say here is, okay, well, firstly, how long will it take the bullet to reach the point it was aiming for, P? Well, we already worked out, just because I said it would be helpful for this last bit, that the distance P away from the origin is this. So we can just do speed equals distance over time. So distance equals speed times time. So time equals distance over speed. So let's do the distance it has to go divided by the speed. This is where it's very helpful that I didn't bother to multiply that out, because this is 35 times 10. So cancel the 35s. 4 times 10 is 40. So this is 5 over 40, which is an eighth. So it takes an eighth of a second for the bullet to reach P. However, the particle itself has going to be going, in that eighth of a second, has gone a little bit further from where it was. So all I need to do is work out how far that particle has gone in that extra eighth of a second it took for the bullet to get to where it was, and just figure out that distance, right? So let's figure out how far has the particle gone in that eighth of a second. So going back to our position vector here, now I don't really need too much of this. All I need to say is that in the eyes, because there's no acceleration in the eyes, it's just traveled an extra u times t. U being this minus 5 root 5 that we found ages ago, it's horizontal component of the speed, times t, an eighth. In the j's, again, this is just the j component of the speed times an eighth. Now the k is a bit more confusing, because just be super careful here. Your initial speed, when you're at p, in the k direction, is 0, because you're at maximum height. So we're not using, so we use the very first things we found for these two, because a is 0, they're never changing. I can always use them. But in the k component, that velocity is 0 at maximum height. So all we have to do is the half at squared, which is, of course, minus 5 is a half a, because a is 10, and then t squared and 8 squared. So that's how far it's gone from P. I ignored this bit as well, because I don't really care how far it's gone from here. I'm thinking about how far it's gone from P. So that's how far it's moved extra. I can simplify that up a little bit. It looks a bit like this if I do that. And now I just need to find, again, because I know the bullet is at P after an eighth of a second, all I need to find is the little distance from P to here, so that it's gone. So all I need to do is find the magnitude of this. I just need to square all of them and add them all up, right? Because that will find the distance that it's gone in that little extra time relative to P, where I started, which is where the bullet is. Okay, so let's do this. Let's just square these things out. So 5 squared is 25 times 5 is 125, and then 25 times 15, and then just 25. I didn't really want to do anything here, so I just put 64s into both of these. And then I factorize that to 25 from all three of the terms in the numerator. And then, okay, well, 5 lots of 64 plus 15 lots of 64 is 20 lots of 64. And then I decided to just ignore this 5. Just ignore it. You know, it's small. I'll just ignore it. This is roughly the same as 25 lots of 20 lots of 64, which is 500 lots of 64. Cancel the 64s, and that's the same as this. Now, 64 times 8 is 512, so this is about 8. And if d squared is about 8, I mean, it's a bit bigger than 8 because I ignored this here. So d squared should be a bit larger than this. Therefore, d is going to be roughly 3. And that was my logic. I think it's okay. I think I got the marks for that, maybe. Who knows? Anyway, I'll see you next time.